Printing. Several types of 3D printing, which include stereolithography, SLA, selective laser sintering, SLS, fused deposition modeling, FDM, digital light process, DLP, multi-jet fusion, MGF, PolyJet. Selecting the right 3D printing process for your application requires an understanding of each process strengths and weaknesses, and mapping those attributes to your product development needs. Let's first discuss how 3D printing fits within the product development cycle, and then take a look at common types of 3D printing technologies and the advantages of each. Determining the purpose of your prototype will inform which 3D printing technology will be the most beneficial. Despite 3D printing being nearly synonymous with rapid prototyping, there are scenarios when it's a viable production process. Often, components for aerospace and medical applications are ideal candidates for production 3D printing, as they frequently match the criteria previously described. 5 3D printing considerations. Like most things in life, there's rarely a simple answer when selecting a 3D printing process. When we assist customers evaluating their 3D printing options, we typically point to 5 key criteria to determine what technology will meet their needs. 1. Budget. 2. Mechanical requirements. 3. Cosmetic appearance. 4. Material selection. 5. Geometry. Polymer 3D printing processes. Let's outline some common plastic 3D printing processes and discuss when each provides the most value to product developers, engineers, and designers. Stereolithography, SLA. Stereolithography, SLA, is the original industrial 3D printing process. SLA printers excels at producing parts with high levels of detail, smooth surface finishes, and tight tolerances. The quality surface finishes on SLA parts not only look nice, but can aid in the part's function, testing the fit of an assembly, for example. It's widely used in the medical industry, and common applications include anatomical models and microfluidics. We use Vipers, ProJets, and iPros 3D printers manufactured by 3D Systems for SLA parts. Selective laser sintering, SLS. Selective laser sintering, SLS, melts together nylon-based powders into solid plastic. Since SLS parts are made from real thermoplastic material, they are durable, suitable for functional testing, and can support living hinges and snap fits. In comparison to SL, parts are stronger, but have rougher surface finishes. SLS doesn't require support structures, so the whole build platform can be utilized to nest multiple parts into a single build, making it suitable for part quantities higher than other 3D printing processes. Many SLS parts are used to prototype designs that will one day be injection molded. For our SLS printers, we use SPRO 140 machines developed by 3D Systems. PolyJet. PolyJet is another plastic 3D printing process, but there's a twist. It can fabricate parts with multiple properties, such as colors and materials. Designers can leverage the technology for prototyping elastomeric or overmolded parts. If your design is a single rigid plastic, we recommend sticking with SL or its SLS. It's more economical. But if you're prototyping an overmolding or silicone rubber design, PolyJet can save you from the need to invest in tooling early in the development cycle. This can help you iterate and validate your design faster and save you money. Similar to SLS, multi-jet fusion also builds functional parts from nylon powder. Rather than using a laser to sinter the powder, MGF uses an inkjet array to apply fusing agents to the bed of nylon powder. Then a heating element passes over the bed to fuse each layer. This results in more consistent mechanical properties compared to SLS, as well as improved surface finish. Another benefit of the MGF process is the accelerated build time, which leads to lower production costs. Fused deposition modeling, FDM. Fused deposition modeling, FDM, is a common desktop 3D printing technology for plastic parts. An FDM printer functions by extruding a plastic filament layer by layer onto the build platform. It's a cost-effective and quick method for producing physical models. There are some instances when FDM can be used for functional testing, but the technology is limited due to parts having relatively rough surface finishes and lacking strength. Metal 3D printing processes. Direct metal laser sintering (DMLS). Metal 3D printing opens up new possibilities for metal part design. The process we use at Protolabs to 3D print metal parts is direct metal laser sintering (DMLS). It's often used to reduce metal, multi-part assemblies into a single component or lightweight parts with internal channels or hollowed-out features. DMLS is viable for both prototyping and production, since parts are as dense as those produced with traditional metal manufacturing methods like machining or casting. Creating metal components with complex geometries also makes it suitable for medical applications, where a part design must mimic an organic structure.